Hello. In this video we're going to be talking about change of basis. We're going to go over a concrete example of changing bases. So I have four vectors written here, C1, C2, D1, and D2. They're all written right now in terms of the standard basis. But I want to think about this other vector I have written here, V, which is 6 times C1 plus 3 times C2. And I'm going to think about V as having coordinates 6, 3, when written in terms of the C basis, where the C basis is made up of these two vectors. I'll also be referring to the basis made up of these two vectors as the D basis, as both of these are bases for R2. Okay? Our goal is to switch from having V represented in terms of the C basis to representing it in terms of the D basis. And another way to state that is I want to write this vector as a linear combination of D1 and D2. So to start out with, I'm going to define a couple of matrices. So this first matrix I'm going to call C, and it's just going to be two column vectors C1 and C2. In other words, C is the 2 by 2 matrix, which is 3, 4 in the first column and 1, negative 2 in the second column. And I'm going to do the same thing for D. So 2, 0 in the first column and negative 1, 3 in the second column. Alright, once I have this, then I can rewrite V as C times the vector 6, 3. Alright, so hopefully this is clear, but if it isn't, just think about the way matrix multiplication works. We're doing 3, 1, so we're doing 3 times 6 plus 1 times 3 to get the top entry, and that's exactly how we get the top entry in the standard basis for V up here. We do 6 times 3, the top entry of C1, plus 3 times the top entry of C2, which is this 1 here, to get the top entry of V written in the standard basis. Same thing for the bottom entry of V written in the standard basis. So C times the vector 6, 3 is V written in the standard basis. Okay? So let's go ahead and write that out. So C is this matrix. Times 6, 3. And I'm going to do 3 times 6, which is 18, plus 1 times 3. Which is 21. And now the bottom entry is 4 times 6, which is 24, plus negative 2 times 3, which is negative 6. So 21, 18. Alright. So I now want to think about what it means to write V as a linear combination of D1 and D2. So I'm just going to use coefficients x and y. Okay. So if V is x times D1 plus y times D2, y is a scalar, then that's the same thing as saying V is equal to the D matrix times the column vector xy, for the exact same reason as we had this before, was this linear combination. Okay, our goal is to find x and y. X and y are the coordinates of v in the D basis. So if we can solve this equation for x and y, then we're done. So how do we solve this? Well, we can multiply by D inverse on both sides. So xy is D inverse times v. Okay, well, we know what v is. And we know what d is. So I'm going to write this as 2, 0, negative 1, 3, inverse, times our vector v, which is 21, 18. All right, so let's go ahead and invert this matrix. You don't remember, you invert a 2 by 2 matrix by first saying 1 over the determinant. The determinant of this is 2 times 3 minus 0 times negative 1. So that's just 6. And then you multiply by this other matrix where you switch the main diagonal and negate the off diagonal. So this becomes 3, 2, negation of 0 is still 0, negation of negative 1 is positive 1. So that 1, 6 times this 2 by 2 matrix is the inverse of this matrix. And that is what we are multiplying by 21, 18. Okay. Just to deal with some smaller numbers, I'm going to factor a 3 out from here and cancel it out with a 3 in the denominator here. So this 1, 6 is going to become 1/2. This isn't changing at all. And these numbers get divided by 3. Okay. So at this point, I'm going to go ahead and multiply this in. So I'm going to keep the 1/2 out in front. 3 times 7 is 21, plus 1 times 6 is 21 plus 6, which is 27. Second entry is 0 times 7, which is 0, plus 2 times 6, which is 12. Okay, so we get 27 over 2 and 6 when we distribute the 1/2 in. Alright, so this column vector right here is just the values of x and y written in a column vector. Our goal was to find what x and y were so that we can write v as x times d1 plus y times d2. And that is our answer. Okay, so now another problem. So same problem, except I've made this 6, 3, an R and an S, just to make it more general. Okay, and I just want to generalize the process that we just went through and point out what we did. So we took this V, which was 6, 3, written in the C basis, and to multiply by C and write 2118, that's the same thing as switching V into the standard basis. So it was in the C basis, the 6, 3 representation, and this new representation, 2118, is the standard basis representation of the same vector V. Okay? We then took that standard basis representation of V and multiplied it, so right here, we multiplied it by D inverse to switch it into the D basis. So to switch from the C basis into the standard basis, we multiplied by C, and to switch from the standard basis into the D basis, we multiplied by D inverse. So just to state this in the same way, if U is A times D1 plus B times D2, so this is the solution now. Our goal is to find A and B. Then AB can be found by just doing D inverse times C times our original C coordinates, R and S. Okay, that's the exact process that we went through. In other words, to translate from C basis coordinates into D basis coordinates, we multiply by this matrix, which is the product of these two matrices. Okay? This matrix is called the change of basis matrix. Okay? And the book writes this with a P, and then it has some extra fancy notation that says that we're translating from, this is a curly C, so this is the C basis into the D basis. Okay? And just to note, these two vectors right here are the basis curly C. These two vectors right here are the basis curly D. So we're translating from the C basis into the D basis by multiplying by this product of matrices, which is the same thing as this in the book. Thank you for watching.